Good day, everyone. Thank you for taking this time to attend this presentation. Today, we'll be discussing our thesis entitled Development and Characterization of PLA-NPCC Composites via Non-Solvent-Induced Phase Separation for Enhanced Oil Spill Remediation. This research was conducted by myself, Mark Lawrence Del Campo, and my co-researcher, Mr. Min Gonsong, as chemical engineering students under the guidance of Dr. Persia Ada de Airo and Dr. Ruth Aquino. Next. So to start off, oil is a fundamental resource in various sectors worldwide, playing important roles in transportation, energy production, manufacturing, and numerous industrial processes. Its widespread use highlights its indispensable nature in modern society. However, this extensive reliance on oil also heightens the risk of accidental spills during extraction, transportation, storage, and usage. The catastrophic consequences of oil spills are well documented, with profound impacts on marine ecosystems, coastal communities, and the economy. One of the most catastrophic instances was the Deepwater Horizon incident in the Gulf of Mexico, which resulted in approximately 65 billion US dollars in cleanup and legal costs. In the Philippines, an oil tanker containing 2 million liters of oil sank in 2006 to a nearby coast, damaging 1.5 hectares of local environment and affecting marine ecosystems, industry, and tourism within the community. These events result in extensive environmental degradation, loss of biodiversity, disruption of livelihoods, and significant economic losses. Next. Given the persistent threat of oil spills and the magnitude of their consequences, there is an urgent need to develop innovative strategies and materials to mitigate their impact and safeguard the environment. Various methods and technologies have been developed over the years to address oil spills and mitigate their impact on the environment. These methods include deploying physical barriers such as booms to contain the spreading oil slicks and prevent them from reaching sensitive coastal areas. Skimmers are also used to mechanically remove oil from the water surface, while manual labor involves collecting and removing oil-contaminated debris. However, mechanical methods like skimming and boom deployment often struggle to contain spreading oil slicks, particularly in adverse weather conditions and rough seas, limiting their effectiveness in controlling oil spill incidents. Chemical dispersants, another common approach, break up oil into smaller droplets, facilitating its dispersion into the water column and enhancing microbial degradation. However, using dispersants raises environmental concerns due to their potential toxicity and long-term impacts on marine ecosystems. Next. Now moving on to innovative materials for oil spill remediation, one of the things is polylactic acid, or PLA, is a biodegradable and eco-friendly polymer that has gained attention for its environmental benefits compared to traditional petroleum-based polymers. One key reason for choosing PLA is its lower carbon footprint. When comparing the CO2 emissions per metric ton of produced polymer, PLA emits significantly less CO2 compared to polypropylene, PET, polystyrene, and nylon. This reduced environmental impact makes PLA a sustainable alternative for applications requiring polymer-based materials, aligning with the global efforts to minimize the carbon emissions and develop greener technologies. Next. Now, this table compares PLA's mechanical properties with common polymers such as PVC, PP, PS, and nylon. The data highlights PLA's well-balanced combination of strength, stiffness, and durability, demonstrating its competitiveness across these key parameters. Next. Now, when surface modified, NPCC exhibits its oleophilic and hydrophobic properties, making it effective in oil spill absorption and water repellency. These characteristics are particularly advantageous for oil spill remediation, where materials must selectively absorb oil while repelling water. The combination of PLA and NPCC creates a composite material with properties tailored for oil spill remediation. PLA serves as a structural role, providing mechanical stability and acting as a matrix to uniformly disperse NPCC. Meanwhile, NPCC contributes its functional properties, enhancing oil sorption due to its oleophilic and hydrophobic nature, it also offers a high surface to volume ratio, improving its interaction with oil. Together, the synergy between the two results in a composite material that balances structural integrity, functionality, environmental sustainability, making it a promising candidate for efficient and eco-friendly oil spill cleanup. Next. Now, for the objectives of the study, our general objective is to develop and characterize the PLA-NPCC composites for oil spill remediation, while our specific objectives include, first, to create PLA and NPCC monoliths with varying SM-NPCC concentrations. Second, characterize the monoliths through morphological analysis and water contact angle measurements. Last but not the least is to determine the absorption capacity of the composites. Next.
The significance of the study aligns with the following SDGs as presented in the slide. For environmental and industrial application, the development of PLA SM-NPCC composites offers a sustainable and effective solution for oil spill cleanup, reducing ecological damage and protecting marine biology while promoting eco-friendly industrial practices. For the field of material science, the study enhances the understanding of PLA SM-NPCC composite behavior, particularly in terms of hydrophobicity, adsorption capacity, and structural properties, paving the way for future innovations in composite materials. For the methodology, we begin with a surface modification of NPCC. In a beaker, 20 grams of NPCC was dispersed in 50 grams of water and kept at 100 degrees Celsius under constant stirring. In a separate beaker, 1 gram of stearic acid was mixed with 20 grams of water and 1 gram of sodium hydroxide. The contents of the separate beaker containing stearic acid was added to the initial beaker and stirred for 1 hour. The beaker was then dried in an oven for 24 hours, producing SM-NPCC. 0.135% of SM-NPCC was then sonicated in DCM for 30 minutes, and then mixed with PLA using a planetary mixer to dissolve the PLA, forming an 18% by weight sample of PLA to DCM. An equal amount of hexane to DCM was then added in a dropwise manner under constant stirring to initiate the NIPS process. The samples were then left to gelate for 8 hours. Then, the samples were immediately washed with methanol under constant stirring for 30 hours and then dried for another 24 hours. Here is a picture of the surface modification process and a picture of one of the monoliths. The following tests were done to characterize the samples. First, we have the optical micrographs, which were done using a flat strip of the monolith and a standard microscope at 100 to 200 times magnification. The water contact angle was used to determine the wettability or hydrophobicity of our sample and involved using a similar strip of the sample and a contact angle goniometer, wherein a micropipette is used to place a small droplet of water for us to analyze the contact angle. For the oil adsorption capacity, our whole samples were submerged in a beaker of diesel for 30 seconds and ensured that no excess diesel that was not absorbed by our sample was weighed.
Now, we move on to the results and discussion. Here, we present the optical micrographs of the composite samples with varying concentrations of SM-NPCC. These images showcase the morphological changes observed in the samples. As the concentration of the SM-NPCC increases, we can see noticeable increase in surface roughness. The composite surface becomes more irregular, indicating the effect of the surface-modified NPCC integration into the PLA matrix. These surface irregularities are primarily attributed to the integration of the surface-modified NPCC particles within the PLA matrix. The particles create disruptions in the material structure, which is evident in the micrographs. Next. Furthermore, a study by Songsang et al. Provides additional insight into these morphological changes. The research revealed that the pore size of the composite materials tend to increase as the concentration of additive materials rises. This phenomenon occurs due to the interference in the fabrication process caused by the additive, resulting in larger pores and greater surface irregularities. The observed increase in surface roughness and findings of Songsang et al. align closely, supporting the idea that the morphological changes in these composites are directly influenced by the presence and concentration of SM-NPCC. Next.
The water contact angle measurements for PLA SM-NPCC monoliths show the positive trend, increasing with higher SM-NPCC content. This trend can be attributed to the changes in surface morphology observed in the optical micrographs, which revealed a progressive increase in surface roughness with the addition of SM-NPCC. Additionally, the inherently superhydrophobic and oleophilic nature of SM-NPCC further contributes to the overall water-repellent behavior of the monolith. The relationship between surface roughness caused by the NIPS process and hydrophobicity can be described by the Casey-Baxter model. According to this model, rough surfaces amplify hydrophobicity by trapping air pockets between the water droplet and the surface, reducing the effective contact area of water with the sample. Here is a sample of our water contact angle results. Here we can see that the approximate WCA reading is around 115 degrees.
Now, let's discuss the results for the absorption capacity. The data shows an incremental increase in absorption capacity with the increasing concentration of the surface-modified NPCC. This trend can be attributed to the enhanced surface roughness observed in the optical micrographs. As the SM-NPCC concentration rises, the surface area available for absorption also increases, allowing for better interaction with the oil. This observation is consistent with the findings of, again, Songsang et al., who reported a similar trend in their study. They found that absorption capacity increases with higher additive concentrations, which, again, aligns with the morphological changes and pore size increase seen in this work. Comparatively, the absorption capacity of the PLA-SM-NPCC composites is comparable to other monolith-based studies, such as hydrophobic polycarbonate monoliths studied by Wang et al. In 2016. Overall, the results demonstrate that the PLA-SM-NPCC composites are effective in adsorption of these materials. Next.
To answer the specific objectives of our study, our conclusions are presented as follows. PLA SM-NPCC monoliths with varying SM-NPCC concentrations, which are 0, 1, 3, and 5%, were successfully developed using the NIPS technique, showing effective incorporation of SM-NPCC and an increase in surface roughness with higher concentrations. Water contact angle measurements confirmed increasing hydrophobicity with higher SM-NPCC concentrations, attributed to surface roughness and SM-NPCC's hydrophobic nature, which enhanced oleophilic properties, making the monolith suitable for oil spill remediation. The adsorption capacity increased with SM-NPCC concentrations from 3.13 grams per gram for pure PLA to 3.48 grams per gram for 5% SM-NPCC, showing improved oil interaction. Thank you very much for listening.